This video goes through solving simultaneous equations using Gaussian elimination, which is also called row reduction. Now, if we have two simultaneous equations, two variables, ax plus by equals u, cx plus dy equals v, we have already looked at setting that up into matrix form, where A is our coefficient matrix, A, B, C, D, X is our variable matrix, X, Y, and B is our constant matrix, U, V. Now, we can combine matrices A and B into what's known as an augmented matrix. So that's A, B, C, D with our line U, V. So we have A slash B. Now, our goal to be able to solve is we want to have an identity matrix on the left. So we want 1, 0, 0, 1, and then on the right-hand side, we'll end up with our solution. Because what this is saying is that x equals m and y equals n. So we're going to be playing with our rows to be able to get this identity matrix on the left-hand side. Now, the augmented matrix may be transformed into an equivalent augmented matrix by interchanging two rows. So we can swap our rows, multiplying a row by a non-zero constant, or adding a multiple of one row to another row. Now, we always put zeros where you need them under the leading diagonal first. Okay, so we're going for this 0 here before looking at the 0 on top. If we have a 3 by 3, then we would be looking at 1, 0, 0, 0, 1, 0, 0, 0, 1, M, N, let's go with P on that side. So we're going to be trying to get these zeros before we look for the zeros at the top, okay? And again, as you can see by this 3 by 3, our x is going to equal m, our y equals n, and our z is equal to p. So again, we're trying to get that identity matrix on the left-hand side. Okay, let's look at some terminology. In this augmented matrix that I have here, the first non-zero entry of a row is called the row leader. So we have 1 in the first row, 6 in the second row, and -1 in the third row. So they're our row leaders. Now, this is known as row echelon form. You can see that at the top, we don't have zeros. Now, we can stop here and use back substitution to find a solution. Now, what I mean by that, if we look at our third row, we have negative z equals -3, so z equals 3. We then have with our second row that 6y minus 21z equals -51. So we can use that z equals 3 by going 6y minus 63 equals -51. Then we can go, okay, well, 6y equals -51 plus 63. That's equal to 12, so our y would be 2. We then go to our first row. We have x plus y plus 2z equals 9. So that's going to be x plus 2 plus 6 equals 9. X plus 8 equals 9. So take 8 from both sides. X equals 1. So therefore, solution is x equals 1, y equals 2, and z equals 3. So that's one option. We could also continue using Gaussian elimination until we have the identity matrix on the left-hand side, and then our solution can be read straight off. So you can see here that we have our identity matrix, which means that we can read our solution straight off. X equals 1, Y equals 2, and Z equals 3. Now this is known as reduced row echelon form. So let's look at an example. Solve the following pairs of simultaneous equations using Gaussian elimination. So we have to set up our matrices. Our coefficient matrix is going to be 1, 2, 3, -1. So just reading the coefficients. Our variable matrix, we have two variables, x, y. And our constant matrix is 4, 5. So bringing that together into our augmented matrix, we have 1, 2, 3, -1, and 4, 5. Now the goal is to get this element here to be 0. So our aim is to get that reduced row echelon form, which with our identity matrix on the left and our solution on the right. So we're going to look at this 3 here, and we need to make it 0. So if you look at our second row and our first row, we have this 1 here. So if I go row 2 minus 3 lots of row 1, that's going to be 3 minus 3, which gives us our 0. So this is very similar to what you would be doing in your elimination method of simultaneous equations. So our first row is going to stay the same. We're not touching it. Then we're going to go row 2 minus 3 lots of row 1. So 3 minus 3 lots of 1. 3 minus 3 is 0. -1 minus 3 lots of 2 is -1 minus 6. So that's -7. 5 minus 3 lots of 4. 5 minus 12 is -7. Okay, now we're going to look at this -7 and we want to make it 1. So we go, what can we do with our rows to make that there to be 1? The easiest option is to just times it by -1 over 7. Or if you want to think about it as dividing by -7, but we're always multiplying. So our first row again remains the same. We're not touching it. I'm going to multiply the second row by -1 over 7. So that makes that 1. -7 times -1 over 7 is 1. So we have our second row exactly how we want it. Now we move to this element here. We want to make that into 0. So if I go row 1 minus 2 lots of row 2, I would make that into 0. So 1 minus 2 lots of 0 stays the same. 2 minus 2 lots of 1 is 0. 4 minus 2 lots of 1 is 4 minus 2 is 2. And then we have our 0, 1, 1 there. So now we can read our solution straight off. So solution is x equals 2 and y equals 1. Now remember to verify your solution by substituting into the original equations. So to verify, we have x plus 2y equals 4. So our left-hand side would be equal to x is 2 plus 2 lots of 1, which is 2 plus 2, which is 4, which equals our right-hand side. For 3x minus y equals 5, Our left-hand side is 3 lots of 2 minus 1, 6 minus 1, which is 5, which is equal to our right-hand side. So we know we're correct. Now, in regards to steps to help you do Gaussian elimination. 1, get 0 at the bottom left. 2, get 1 at bottom right. 3, get 0 at top right. And 4, if required, it wasn't required here because we already had that 1, but we would need to get 1 at the top left. So the next example, solve the following pairs of simultaneous equations using Gaussian elimination. I am going to do this in the next video. So I want you to try and solve this before watching the next video.